I would like to just take a brief moment to, as a team leader, to thank every one of my team members with a short round of applause for all the hard work that they've done. So to continue, so to give you a quick system overview, our goal of this project was to create an expandable robotic arm cell consisting of 2 robotic arms that can be controlled with a handheld analog game controller. The purpose of this is for it to be able to store the user movements and replay them in a semi-autonomous fashion with a 180-degree workspace. This is the system block diagram that kind of gives a quick overview. It doesn't do the true system justice of how much work that we put into it, but just kind of give a concept of understanding. We created the HMI system, a human-machine interface, which is actually this left portion over here of the block diagram. What this is responsible for doing is conducting the main controls, inverse kinematics, or kinematics, to push these commands to the robotic arms themselves, which are connected via this Arduino in servo control. Connected to this are the 6 servos of each arm, actually 7, that can mimic and display and orientate the arms as we desire. The major works consisting of this project, of course, are the human-machine interface, which I just previously mentioned, the servo control driver, the servo feedback modification, the Python inverse and forward kinematics programming, the communication between the Raspberry Pi and Arduino systems, and a 3D printed end effector of our home-built design, and last but not least, the robotic arm construction. So to do a quick caption of all these aspects and how much actually went into it, the servo feedback modification, what that was designed for was to actually gain position feedback from using the onboard potentiometer of each servo. So short of having to buy really expensive servos that can already tell you where they're at and everything, we figured we'll go on the cheap end, tap in a quick wire to the potentiometer, and then we can calculate the feedback. So on that same note, another very impressive aspect are the forward and inverse kinematics, which are responsible for controlling the arm itself. This was very impressive, and thanks to Brad, Andrew, and Aaron, they were able to make this possible. So what it does is it interprets the user's controls from the game controller itself and manipulates these to specific angle orientations to move the end effector to the desired result. And as a whole, we also made, Josh has made these fantastic brochures. So if you guys would like a little bit more detail about the abstract, minimum success criteria, and everything else about our project, you're more than welcome to see it at our demonstration.
He's a good presenter.
And the way we would like to play in this demo, we would actually like, although it runs completely on our HMI, it runs much slower. So for the sake of timing, we're going to do the exact simulation on the PC. We're going to break this demo up into 2 portions. We're going to show the record and playback functionality of 180-degree workspace by controlling one arm and then playing it back to the other one. And for the second half of the demonstration, we're going to control both arms simultaneously to pick up this step. So, Brad, would you like to go from there? So he's actually recording these movements of this one arm right now. Now we're going to play it back on both arms. demonstration. Now the second one, Brad's going to actually control both arms to simultaneously pick up this ruler stick thingamabob. Yeah. Which, mind you, Brad is by far the best controller of these arms. It gets excited sometimes. But during practicing, it actually picked up the screwdriver and flung it at Brad's head. It was pretty entertaining. This is the other one?
Yeah. I was going to say just turn it underneath.
That was my fault. Oh, excellent.
Be here all night.
Out of range.
Okay, you can come back to this team,